Thank you. I'm going to split my talk into 4 stages. The second and third are extremely brief. So I just want to concentrate first on the UK energy problem, and then finally at the end just solving it. So, or trying to anyway. So this is showing the UK's overall final metered energy according to Bere's, the ECUC, the latest ECUC, which you can download from the web, ECUC 2018, and it shows that the metered energy consumption has been increasing. Overall, total UK metered energy consumption has been increasing for several years on temperature-corrected basis. Exactly what we would hope wouldn't be happening. And then, if we look at another graph from Bere's, the domestic energy consumption accounts for 28% of all UK energy use. That's what it says. And on the graph there, you can see that only up there with it is transport. But it's actually a little bit more worse than that, I believe, because elsewhere in the document it says that service, 15%, includes much of the heat sold to domestic customers. And this is an extract from that wording. So it says, highlighted in yellow, previously much or heat sold within the domestic sector has increased dramatically in 2017, and then previously much of the heat sold was included within the services sector. So I looked at the previous year, but the previous year looked exactly the same on the graphs. So I don't think it, my hunch is it hasn't actually gone across to the graphs to avoid confusing the politicians. So we might be finding the domestic energy consumption is higher than that. I'd love to speak to people putting together the ECUT report in more detail to discuss that. So it's somewhere around between 28–30% or so of the total UK consumption is going into buildings, and 80% of that is going into heating of those buildings. And then if you look at another Bere's graph showing the division into fuels, you'll see that gas on this graph is by far the highest consumed material or product, fuel in the UK. Petroleum, and most of that is going for heating of buildings. Petroleum is mostly for vehicles, it says in the small print elsewhere, by the way. And then if you look down near the bottom, the key point I want to make, the second one from the bottom, is electricity. So if heating of buildings isn't greatly reduced, really significantly reduced, while in preparation for decarbonising the energy supply of buildings and transport, and I know John's going to be speaking more about this shortly, then we could end up with some, I've done a really, really rough assumption, maybe 500% increase in energy consumption. John may have more accurate figures than that, but that's taking into account, that's my rough sum, taking into account increased efficiency between petroleum vehicles, combustion engine and electric vehicles, and gas moving to electric heat pump. So my conclusion is on this first section of the talk is that to avoid disaster, which is not having enough energy, we must more or less get rid of heat in buildings, and then really there's no realistic alternative. So very, very briefly, just my practice, we exist in order to try and solve environmental, ecological problems. Of course, we need funding from clients who share our objectives and want to use us as a vehicle to give them homes, but also to show how those homes and those commercial buildings could be exemplars for the rest of the industry. And I won't go into this at all, but basically we try and do convincing design as well as high performance. We're really keen on the technical delivery of buildings, getting those right, and R&D, Some of it in the past has been funded by the Technology Strategy Board, now Innovate. Currently we're funding all the research you'll see today ourselves. It's difficult. So brief note about Passive House Plus as well, very brief on this. This shows the three different, if you look on the left-hand side of that chart, Passive House Classic, Passive House Plus, and Passive House Premium. And then if you move along to the second column from the end on the right, the key thing there is targeting reduced primary energy consumption. Primary energy, talking about the energy at source. So if it's coming from a power station, then there's about 10% loss between the power station and the site. But if you're talking about the fuel also going into the power station, I believe you're talking about a factor of about 2.7 generally across all power in the UK. We do have really strict requirements that we place upon ourselves to measure and ensure that space heating demand in a predictable, in an average user is going to be at a certain limit. We must make sure that the buildings are draft free so that you don't spend a lot of money on insulation and then find that all the heat's being washed away by drafts, cold drafts running through the house in the winter. We also take serious concern over maintaining summer temperatures. And the last slide in this little section, that it's not just about numbers, it's also about quality. And one of the biggest differences, I think, in the UK between the cost of a passive house today with an average contractor, general run-of-the-mill contractor, and the cost of doing an ordinary building is actually the skills difference. The actual difference in materials is very small. We're talking about 5 or 10%, but often it goes way above this because you're talking about a comparison between, I hope this doesn't offend anyone, but I have got evidence. I visited did a report on a big house builders project just recently. People who really don't know what they're doing compared to people who really have to know what they're doing in order to get a certificate. And obviously, many contractors really do know what they're doing. And I'm not trying to be too general, but there is a significant skills gap that translates into costs. So between passive house and ordinary buildings, the blue chart, the blue columns are showing the average standard UK classic building regulations house through the winter period rather, and below that you'll see the calculated emissions for the Passive House Plus. This was a report that was done by Energelio consultants working with us before we did Lark Rise in order to size the PV and battery storage, and it's been proven in use. So moving on to this single project to try and test the theory. We've found after 2 years of monitoring, and the monitoring is available on our website, free to download, both the Energelio original analysis and the as-built monitoring. It's due to be updated with new data when we've got time. Generates 2.5 times more energy than it uses annually, and exports over a year 10 times more energy to the grid than it imports. And that, if that sounds confusing, that'll be a little bit clearer, I think, in a minute when we look at the graphs. So on the left, that chart shows the average UK house needing to import around about 200 kilowatt hours of energy per square meter per annum. And on the right, it's showing the delivered results from Lark Rise, which has an import of 3.38 kilowatt hours per meter square per annum and an export of 34.6 kilowatt hours per meter square per annum. So that's not just taking heating off the grid. That's everything, by the way. That's even power loads, sockets, heating. It's an all-electric house. It's a 98% reduction. It's basically taking the building off the grid for all intents and purposes. And now I'm just going to run through a sequence of slides here. So these red dots on the slide here, or I'm going to build up this graph, I should say. These red dots on the graph here, and incidentally in the horizontal axis, right down at the bottom you can see, I'm sorry it's rather small, 3 weeks during September 2018. And on the left-hand side, it's kilowatt hours of energy used or stored, used being above the line, stored below the line, each day during those 3 weeks. So the typical building is, from the data that we've been provided by our energy consultants, is shown in the red dots. Then secondly, I'm going to show you there on the Lark Rise the final energy use. This is what the building requires. Now, a lot of that you'll see in a minute is coming from solar, but this is what the building requires on each of those days. And by comparison, it's a lot less, but it's going to get a lot less still. This is showing on each of those same days the solar energy produced. So we're at the kind of approaching the turning point of the season, of the year, I should say here. And our solar energy is roughly in balance with the amount of energy required by the building, perhaps a bit more some days. And then this is showing the battery storage and use. So above the line is the energy that the battery is putting into the building, and below the line is the energy that the building is storing. And then hopefully you can just see that beside the little grey. I'll go back and do it again just so you can see them appear. Those little grey marks are the grid energy. Above the line, which is virtually invisible, is the energy taken from the grid, and below the line is the energy put back into the grid. So the energy from the sun is first going into into the battery, and then on the whole it will only go into the battery, into the grid, once the battery is full. So in conclusion, or making a sort of a detailed comparison there, I took the first one. If you look at the sorry, I haven't got a pointer or anything, but if you look at the first tall graph, there's a 73 times less power in that between the power taken from the grid by this building on that particular day and what a normal building would. And then the next one along actually used even less from the grid, so I thought it was going to be a less example, but actually it's even greater. So 99% less grid power than the ordinary house. And then if you look along the notes at the bottom, 18 times more power exported to the grid than imported on one day, 11 times the power on another day, and so on. So these are really dramatic results that increase the difference between the ordinary building and the passive house when you get to the passive house plus, or the passive house's power station. And then we're monitoring these in real time. Actually, it's a wonderful little app by Tesla, because we have a Tesla battery, and we swapped over to the Tesla controls, which decision-making controls that then send us this information, which I don't know if I've got time to go. Yeah, I've got 5 minutes. So looking at the left one, just to help explain it, we've got starting from the left-hand side of the left-hand column, in green we've got battery power until 3 a.m., which was left over from the night before. This is actually just a few days ago. The team here were incredibly generous at allowing me to load these up last night. Last Saturday, we had battery power until 3 a.m., and then mains power from 3 a.m. until 8 a.m., and then solar power. The sun came up about 7:45 and basically took over. There's a little bit of blue in that trough, which is a bit of mains power being used because there's not enough solar, and then the solar kind of takes over. And then the green below the line is where the system is starting to put power into the battery, and that's usually in those little troughs between demands. So where there wasn't demand, one of those blue demand spikes, there's spare energy to go into the battery. And then just to bring it right up to date, on Monday and Tuesday this week, we've got mains power through until 8 a.m., solar power then kicking in, slightly lower demand from the building during the day. We've got that tiny little ripple. It's been very frustrating, even in the middle of the summer. We can never get rid of that tiny little ripple, which I note as residual power for the controls. And that's because the controls draw about 200 watts of power on and off. And that's because if the controls were on the battery and the battery went flat, then you wouldn't have any controls. So it has to be mains powered controls. I'm sure it's possible to get around this in time, but that's what we have to live with for now. And then you see from about from about 4 p.m. the sun goes down, and above the line green means the battery is supplying the energy, and the battery is actually supplying the energy. There's a demand going on all night. I have done sort of soft landings discussion, but I really don't quite know yet whether these are lights being left on all night or whether someone's working all night. But then and it varies. So sometimes it does go down to 200 watts, and this is about I think it's about 350 watts. And then over on the right-hand graph, you'll see that 5 out of 7 days this last week, we've had solar energy exceeding the grid energy. So more solar energy has been going into the building than grid energy. Now, again, I'm not going to go through these. These are kind of just throwing them out there. If you want to take a picture or get it off, presumably, the web, we can really happily have a debate. These calculations are unchecked. They require peer review. I've done them completely honestly, as best as I can. I can run through, got 2 minutes, and this is nearly the end. So, Lark, I've calculated the export for one building to get to a kiloton of oil equivalent. That very first graph I showed you, the UK kiloton of oil equivalent primary energy requirement is 130,000 kTOE. These are metered, and I haven't attempted, it's terrible, but I haven't had a chance to try and relate one to the other. But all UK passive houses power stations, so say all 25 million homes in the UK, and really what I'm getting to is what's cheaper, doing this or building new power stations. So say government accepts we've got a climate emergency, it's like a military emergency, you don't ask the money, you don't ask how much it's going to cost you, you get on and do it. Retrofit program for 25 million homes. The energy savings you will achieve to this standard, that's not the power generation, the energy savings, 21 times bigger by my calculations than Hinkley Point C power station. And the savings are 9% of the UK's current total final energy demand. That's total. Of course, it's pretty well 100% of UK's domestic energy demand sorted, gone. All UK houses as passive house power stations, and including the the first was the generated energy. Beg your pardon, was 9%. The second column is the efficiency savings, and there we basically have a saving of 54 times bigger than Hinkley Point C. I love someone would check this, and I do have a grid advisor who had a conversation with last night, and we're going to meet and check these. Savings of 24% of the current UK total energy demand. Combine those, you get a 30% of total UK energy demand. Look at the costs. If my sums are right about the cost of nuclear, and I haven't had a chance to look at the cost of renewables, and hopefully they'll be better. And I'm of course not looking at the point of building new gas power stations or anything like that, because that would be defeating the whole object. But I reckon that I haven't got time to go through that, but I reckon it's significantly cheaper. We would have £360,000 per home at the rate of spending of a nuclear power station, and I think it's going to be 7 times cheaper than that, or more, to retrofit buildings per kilowatt hour at scale than to build new power stations. Economical viable delivery. So just 3 or 4 slides, some conclusions. Economically viable, therefore, delivery of useful prolonged net plus energy from a powerhouse can only be realistically achieved if the starting point is a building that is as economical to run as a passive house. Otherwise, if you remember that graph with the red dots, we'd have to multiply the amount, and we're talking about 70, 80 times as much energy needed in September. We'd need 70 or 80 times as many PV panels to achieve the same result. It's just not economically viable unless you cut energy demand in the first place as your starting point. So there's a potential to reduce UK domestic energy demand, I believe, from what I've shown you, by 100%. Basically get it off the grid. Obviously we're going to be connected with the grid, and I'm talking in net terms, and I haven't looked at peak load because I haven't had time, but that's another thing that we should be doing. So this equates to approximately 30% of total UK energy consumption. Total cost, I believe, is cheaper than power stations. And also, if you choose between investing in homes or investing in a power station to the same effect, I mean, isn't it a no-brainer? Investing in retrofit homes will yield multiple benefits to people and the wider environment that will last at least 200 years. By comparison, the same investment in power stations is estimated to last only 65 years, but does it provide better homes for people? No, of course not. So it's a no-brainer. Thank you.